Physics in motion. Physics in motion.
Welcome to Physics in Motion. Today we are looking at the nature of energy, work, and power.
Thanks for having me back. This is a really fun topic.
Yeah, I'm super excited for this deep dive because, we're welcoming everyone, whether you're a high school student, maybe a 9th or 10th grader battling through integrated chemistry and physics right now.
Right, or just, someone who's insanely curious about how the universe actually operates.
Exactly. Anyone listening, you are in the right place. Because today our mission is to unpack the universe's ultimate accounting system. We've got this whole stack of module notes, diagrams, mathematical examples.
It's a lot of material to go through.
It is. But so I kept thinking about energy from the sources as like a video game stamina meter.
Oh, I like that. A stamina meter.
Yeah, because without energy, absolutely nothing happens, right? Like the universe would be entirely frozen.
Completely frozen, yeah. It's the prerequisite for literally anything occurring.
So to understand the stamina meter, we basically have to figure out how physicists track it.
Right. And to do that, we first have to define what we're even tracking. We have to draw a line in the sand.
Okay, before we draw lines, let's just clearly define energy based on the notes. It's a measurable physical quantity, right?
Yes. It's a measurable quantity that describes the capacity to do work or to produce heat.
Produce heat. Okay. So then you mentioned drawing a line in the sand. The notes call this the system boundary.
Exactly, the system boundary.
And I really want to push back on this concept for a second because does a system boundary have to be like a physical wall, like a literal box you put something inside?
Oh, no, not at all.
Because the analogy in the sources, it asked, is it really just like trying to balance a budget without knowing which bank accounts belong to you?
That is exactly what it is. The bank account analogy is perfect. It's just an imaginary line.
Okay, so it's totally abstract.
Yeah, it's an imaginary barrier separating the specific thing you want to study, which is the system, from, well, absolutely everything else.
This is the environment.
Right, the environment. And the whole point of physics accounting is tracking energy moving across that imaginary line.
So, let's use the bowling ball example from the material. If I'm rolling a bowling ball down a lane, the ball itself is my system.
Yep.
And the lane, the air, the pins, that's all the environment.
Exactly. So what happens when the ball hits the pins?
Well, they scatter everywhere.
Right, because energy just transferred across your imaginary boundary. It left the ball, the system, and entered the environment.
Oh, I see. And you can trace this through different forms too, right? Like the energy transformation diagram we have in the notes.
Oh, the wind turbine one?
Yeah, so you start with wind, which is kinetic energy, and that spins the turbine.
Which is mechanical rotational energy.
Right, and then that rotational energy powers a generator.
Taking it from mechanical to electrical energy.
And then finally, that electrical energy runs to a bulb and it transforms into light and heat.
Exactly. So energy is constantly crossing boundaries and changing forms. It's the currency of the universe.
Okay, so energy is the currency and the boundary is the bank account. But how do we actively transfer that currency? Like, how do I make a deposit?
Well, that introduces the concept of work. And this is where people get really tripped up.
Because of the strict physics definition.
Yeah,
right?
the physics definition is shockingly strict. In everyday life, we say we go to work or work on a puzzle.
But in physics?
In physics, work is strictly the primary mechanism for transferring energy into or out of a system.
And the formula for that is work equals force times displacement.
Right. W equals F times D.
And both work and energy are measured in joules with an uppercase J.
Correct. And force is measured in newtons, which is an N. And distance, or displacement, is in meters.
Okay, so newtons and meters make joules. Let me throw a concrete example at you, literally. The concrete wall scenario.
Oh boy, the classic wall scenario.
Yeah, because this blew my mind. Let's say I go up to a heavy concrete wall. I push it with all my might for 3 solid hours.
You're going to be very tired.
I am exhausted. I'm sweating, my muscles are burning, and you're telling me, based on the strict definition, that I did 0 work.
0 work. Absolutely none.
But I mean, if I push a wall for 3 hours, where did my energy go if not into the wall?
It's all about that equation. Work equals force times displacement.
Right.
Did the wall move?
No, it's a concrete wall.
So your displacement is 0. And mathematically, any force, no matter how big, multiplied by 0 is 0.
That is incredibly frustrating.
It is. But in physics, no movement means no energy was transferred to the system. You expend biological energy, sure, you generated internal heat, but you transfer 0 energy to the wall.
Okay, so the wall gets none of my stamina meter.
Exactly.
Let's look at an example where someone actually accomplishes something then, like the first math example from the module notes.
The robotics cart, right?
Yeah, so a student is pushing a robotics cart with 45 newtons of force, and they push it for a distance of 12 meters. We are solving for work.
So we just plug those into the formula. Work equals 45 newtons times 12 meters.
And 45 times 12 is 540.
Yep, 540 joules of work. That student successfully transferred 540 joules of energy into the cart system.
Okay, that makes sense. But what if we know the work and the force, but we don't know the distance? Like the second math example with the theater winch.
Right, because algebra lets us rearrange the formula.
So the notes say a theater winch does 3,000 joules of work pulling a heavy prop, and it uses 150 newtons of force.
So if work equals force times distance, then distance equals work divided by force.
Got it. So 3,000 joules divided by 150 newtons.
Which gives you 20 meters.
Okay, 20 meters, that's really clean. It's just a totally logical accounting system.
It is, but there's a catch. We only know how to calculate the total amount of energy transferred, which is work.
Right, we don't know how fast it happened.
Exactly. Doing a massive job over an entire year is very, very different from doing that exact same job in 5 seconds.
Oh, so that rate of transfer, that's what we call power.
Yes. The need for speed. Power is strictly defined as the rate at which work is done or energy is transferred.
So the formula is power equals work divided by time, P equals W over T.
Yep. And while work is in joules, power is measured in watts.
Watts. Okay. So I loved the 50 gigabyte file analogy in the notes.
It really makes it click for a lot of people.
Yeah, because if you think about transferring a massive video game file, a 50 gigabyte file, it takes the exact same amount of work to move that data on an old dial-up connection as it does on a modern fiber optic connection.
The total data moved, the work doesn't change at all.
Right. But the fiber optic just has so much more power, it takes way less time.
Exactly. Less time means more power. Another great way to think about it is the staircase analogy.
Oh, walking versus sprinting up the stairs.
Right. Imagine you walk up a flight of stairs. You're moving your body weight against gravity over a set distance.
So that's a set amount of work.
Yes. Now imagine sprinting up those exact same stairs as fast as you can.
I mean, I'm going to feel completely out of breath. My legs will be burning.
But did you do more work?
Well, according to the strict physics definition, no. Same body weight, same height of the stairs.
Exactly. The work against gravity is identical. You feel out of breath because sprinting requires a much higher power output. You demanded that your body transfer that same amount of energy in way less time.
That is wild to think about. That exhaustion is about power, not work.
Yeah, it completely changes how you view physical exertion. Let's look at math example 3 to see the numbers in action.
Okay, this one is an electric motor lifting an elevator. The motor does 12,000 joules of work in 4.0 seconds.
So we're solving for power. Power equals work divided by time,
So that's 12,000 joules divided by 4 seconds.
which is 3,000 watts.
3,000 watts. Okay, that actually brings up a really interesting dilemma from the diagrams in the source material. It was labeled an engineer's decision.
Oh yes, the trade-offs in machine design.
Right. It said engineers basically have to choose between option A, which is low efficiency but high power, and option B, which is high efficiency but low power.
It's the ultimate engineering headache.
Yeah, can you, connect this to the real world for us? Because when would you ever want low efficiency?
Well, think of a drag racing car. You want explosive, instantaneous speed.
Right, maximum power.
Exactly. Option A. You need high power to do a ton of work in just a few seconds. But the trade-off is terrible fuel efficiency. You burn through gallons of fuel in seconds.
Right.
But for option B, think of a hybrid commuter car.
Like a Prius or something.
Yeah. It's incredibly efficient with its fuel, but it has low power. It takes a long time to do the work of getting up to highway speeds.
Okay, so you can't have both. You have to balance the total work you need done against how fast you need it done.
Precisely. You have to design for the specific real-world application.
Okay, well, speaking of everyday applications, let's wrap our heads around how these variables interact in our daily lives. Like with something we all use, the microwave.
Quintessential power box.
Math example 4 from the notes focuses on exactly this. We are solving for time.
Right, so we rearrange the power formula. Time equals work divided by power.
Okay, so the scenario is you have a microwave with an 800 watt power rating, and it needs to do 24,000 joules of work to heat up some leftover pizza.
That's a lot of joules for a slice of pizza.
Right, but so the math is 24,000 joules divided by 800 watts.
Which gives us 30.
30 seconds. So you are transferring 24,000 joules of energy in half a minute.
Exactly. It's a great example of how power ratings on appliances actually tell you how fast they can do a specific amount of heating work.
Okay, let's run through a couple quick review concepts from the source material just to cement this.
Sounds good.
First one, a dog is pulling a sled with 30 newtons of force for 10 meters.
That's just work equals force times distance. 30 times 10 is 300 joules of work.
Nice. Okay, second one. A motor with a 100-watt output operates for 5 seconds. How much work is done?
Well, since power equals work over time, then work equals power times time.
So 100 watts times 5 seconds.
Right, which equals 500 joules of work.
Okay, I think I've got a handle on the math, but I have a theoretical pushback for you based on these review questions.
Bring it on.
Let's go back to a guy pushing a heavy crate, the fast-paced crate scenario.
Okay.
Let's say this guy pushes a crate 10 meters across a warehouse. Then for the next crate, his boss yells at him to hurry up.
Typical.
Right. So he pushes the second crate the exact same 10 meters, but he pushes it twice as fast. What changes?
Well, think about the work formula first. Force times displacement.
The force to push the crate is the same. The displacement, 10 meters, is the same,
So the work stays exactly the same.
even though he ran.
Yes, speed is not in the work equation. He did not do a single extra joule of work.
Wow. Okay, so what did change?
The time. He did it twice as fast, meaning he cut the time in half.
Oh, and since time is on the bottom of the power equation.
Exactly. If you divide by half the time, the power doubles. The vital distinction here is that the work stays exactly the same, but his power output doubled.
That completely reframes how I look at physical effort.
It's pretty profound when you really internalize it.
Yeah. And as we're wrapping up this deep dive, that actually leads perfectly into our final provocative thought for everyone listening.
Oh, right. Leaving the listener with something to chew on.
Yeah, because we want you to think about your own body as a system boundary.
That's a great way to view it.
Right. Every single time you move, you are a machine actively transferring joules of energy into your environment.
Whether you're lifting a book, walking to class, or running a marathon.
Exactly. So as you go about your day, consider this. Are the physical tasks you're struggling with a problem of total work? Like, is the job just too big? Or is it simply a lack of power?
Are you just trying to do the work too fast for your personal engine?
Yeah. Maybe you just need to slow down and lower your required power output.
It's a very practical physics lesson.
It really is. Well, before we officially sign off, I need to give a massive energetic shout out directly to the Geeky Gamer Science teacher.
Yes, absolutely.
Thank you so much for creating the foundation for this deep dive. The module notes, the diagrams, the examples, it was all incredible.
It made explaining the accounting of the universe very easy.
It really did. And to you listening, if you want to officially increase the power output of this show, we need you to smash that like button on the video and subscribe to the channel.
It only takes a tiny amount of work to click a button.
Exactly. A fraction of a joule, but it generates massive power for us. Thanks for joining us for this deep dive into energy, work, and power. We'll catch you next time.
Kinematics calls, the journey has begun. Velocity and vectors, second to none. From rest to speed, force and acceleration, physics in motion. Physics in motion.